Okay, today I'm going to talk about reflection, transmission, and interesting physical phenomena. Okay, some of these might have been covered in your undergraduate course if you've had a undergraduate course in electromagnetics, and some of you might not have this background. So this will be like a revision for many of you, but new stuff for some of you. So this is a wonderful stuff because we are going to obtain closed form solutions from full-fledged Maxwell's equations. We started out with Maxwell's equations in 3 dimensions, and then we simplified Maxwell's equations into transmission line equations or telegrapher's equation. And things are a lot simpler there, but now we're going to solve Maxwell's equations in their full glory. Okay, so we begin by solving the reflection and transmission from a single interface problem. So the problem that we're going to discuss will look something like that. And we assume that we only have a single interface between 2 media, medium 1 and medium 2. Okay, and that we have solutions to Maxwell's equations in region 1 or medium 1. And then we have solutions to Maxwell's equation in region 2. And we will use physical insight to guess how the solutions would look like in these 2 regions. And then we mesh boundary conditions to obtain the unknown coefficients. Okay, so let's begin by starting the derivation. And we like to guess the solution in region 1 consisting of plane waves. Plane waves propagating in this manner in region 1. And then a reflected plane wave that will propagate in this manner with a k vector or the beta vector pointing in that direction. And then a transmitted wave in region 2 propagating in this direction. So we assume the TE case for simplicity. The TE case is also called the perpendicular polarization. Because in this case, the electric field, as you see from the picture on the left, is pointing out of the paper. And hence it is perpendicular to the paper, and it's called a perpendicular polarized wave. And sometimes it's also called a TE to Z wave. Okay. It is actually with respect to the Z axis that this electric field is transverse. Because in a homogeneous medium free space, you can just say TE and it's well understood. But in the case where you have an interface, you have to sometimes specify that it is TE to Z. So we can write down the solution in region 1. Okay, the solution in region 1 for the incident wave would be something like a Y polarized wave. The electric field is polarized in the Y direction out of the paper, and then it has a certain amplitude, and then it propagates like a plane wave. And in order to make it propagate like a plane wave, we put in this phase factor that you have learned in lecture 7, for instance. Okay, and if you write out beta I, okay, beta I would be something that points in that direction that you have seen is has a positive X component and a positive Z component. Beta I would be something like a vector with positive X component plus a vector with positive Z component. Okay, that's how your beta I would look like. And if you substitute that in, you will get the fact that the wave field written in greater detail, if we do the dot product and the exponent, and then I will get Z. Okay, if I plug in the proper components, I get this to be my field in region 1 for the incident wave. And then in region 1, I have a reflected wave as well. And that reflected wave is with a beta vector that propagates in that direction. So beta R would have a positive X component, but it will have a negative X component, as you can see from the picture. Okay, it has a negative X component, a negative Z component. So when they write down the Z, must, well, just put down the sign and call that to be that, okay? And then when you write this down, the reflected wave will have an unknown amplitude. And we do not know what the amplitude is. Let's call it RTE. So this unknown amplitude we call E0 times RTE, okay? Okay, so that is the unknown amplitude. And then when we write things out in gory detail, we will have to put in this thing, and then the beta R vector dot with R. This will represent a wave that is propagating in the desired direction that we show on this transparency on this slide over here. And then we can also write down ET, the wave in the transmitted region. It will still be white polarized, but then with an amplitude multiplied by TTE, okay, and then it will have a beta vector of beta T, and you can write down beta T. Beta T would very much be like beta I, pointing in the same direction. Okay, pointing in the same direction with positive Z component and positive X component. And then if you put these things out, it looks pretty complicated, a lot more complicated than transmission line theory. But we have two unknowns here. The unknowns are RTE and TTE. Okay, so what do you think we should do next to find these two unknowns? We will have to mesh boundary conditions. We have the electric field equations. We can mesh boundary conditions for the electric field. And what would the boundary condition for electric field at this interface in terms of boundary conditions? Does anybody know, or does somebody want to turn on your mic and tell me what the boundary condition should be at the Z equals 0 interface, which is this point over here? What should be the boundary condition there that we should impose?
The tangential part of the electric field should be continuous.
Wonderful, yes. Tangential part of the electric field should be continuous, and the tangential component of the electric field is a Y component. If you think about Y component, it is parallel to the surface, and hence these are all tangential components, and you can impose them to be continuous, okay? And you can get that quite easily. You can put them down. You can make sure that this thing plus this thing, which is a total field in region 1, should be equal to that, okay? So you can immediately see that the boundary condition should be 1 times this factor. Okay, let me write down this factor. I'm going to write down this factor explicitly, setting Z equal to 0, okay? So if I write down the factor, it would be e to the j beta ix x. But because I set Z equal to 0, the exponent to the Z just becomes 1. And then I have to add in the reflected wave. Okay, I do the same thing to what I have in the exponent there. And again, because of the fact that I set Z equal to 0, this component disappears. So if I add the first two waves, EI and ER, and then set Z equal to 0, I get this to be the tangential component of the electric field in medium 1, and then in medium 2, I will have to write that down. I would do the same thing. E naught is common to all the three expressions, so I don't have to write E naught down. And then I would write down the thing in the exponent now. Now I'm going to set z equal to 0, so this term will disappear. Okay. And I need this equation to be satisfied. Okay, I need this equation to be satisfied, but apparently this is not enough to enable the solutions of the Maxwell's equation for this problem. So we need something else. We need something in addition to what we have seen. And then we need the magnetic field. Okay, so we would derive the magnetic field next. In order to do that, we have to go to Maxwell's equations and use Faraday's law. Curl of E is equal to J omega mu H with a minus sign. I better not forget my minus sign, because we often have to hop between the optics community and the engineering community. In the optics community, the time convention is this. In the engineering community, the time convention is this. So you have to make sure that you have to learn how to switch between minus I and J. Okay, so in order to simplify this equation, we are only dealing with plane waves, so we can make the assumption that the del operator, because we are only working with plane wave, becomes J beta. Okay, and Maxwell's equations just becomes J beta cross E for the left-hand side is equal to minus J omega mu H on the right-hand side. That is what becomes of Maxwell's equations or Faraday's law. And then now I can work on all the components of the magnetic field. I can work on my HI first. So you see how tedious this is when you work with full-fledged Maxwell's equations. And if you work on this term, you will get that this should be beta I cross EI over omega mu 1, because I'm dealing with region 1. Okay. And you can go through the details, which I don't feel like doing. I can do it if you want me to. I can actually go through the detail of doing this vector algebra. Okay, let me just work out the detail of this. And this would actually be something like beta I cross y hat E naught e to the minus j beta I dot r over omega mu 1. Okay, and if you go to the vector algebra, you can show that if you take the cross product properly, you don't have to use a determinant to do this cross product. Many students, when they come to having to take a cross product, they will write down the determinant rule. And instead, I would suggest that you just use the very simple rules that you know for x cross y is equal to z hat, y cross z equals x hat, and then z cross x is equal to y hat. And then the rest of the cross products are 0. Okay, we just use this very simple rule. You can use the distributive property of cross products and do it term by term, and then you will obtain the fact that this is actually just equal to z hat beta ix minus x hat beta iz over omega mu 1. Let me write my omega mu 1 properly. E naught e to the minus j beta I dot r. Okay, this would be what I have for HI, and you can get the hang of it, and you can see how complicated it is. Okay, so I will not do the other components, but you get the hang of it. You know what I'm talking about when you have to do this in gory detail. You just have to do this very carefully, so you can actually go and work out your reflected field, HR. Okay, HR will be given by beta R cross ER over omega mu1, and then you can do the work yourself at home, and then you can go and look for HT, which would be beta T cross ET dot omega mu2. Remember, I have to replace mu1 with mu2 because I'm in region 2. Okay. So, so we have this additional magnetic field, and we will have to mesh the second boundary condition. The second boundary condition is naturally following from Ampere's law, which says that tangential H field has to be continuous. The first boundary condition we had followed from Faraday's law. Okay, so if we put in the second boundary condition, what we would have is that we have to add the components of the field, magnetic field on the region 1, and then components of the magnetic field in region 2 in mesh boundary condition, and you will get the fact that you will have something that looks like this, that the incident magnetic field in region 1, if you work out the detail, I work out the detail for one case over here, okay? The tangential component will be just the X component. The Z component is not tangential, so I can just ignore that. So if I write down the tangential component for region 1 for the incident field, and then set Z equal to 0. And then divided by omega mu1, that is the HIX for the incident field, and then you would have that for the reflected field, there's a sign change. You have to be very careful about this because the beta Z would change sign. Okay, because for the reflected field, the beta points outward. So the beta Z has a different component in sign compared to the Z component of this spectrum. So there's a sign change, and you have to be careful about this. If you don't take care of this sign change, you will not get the correct answer. So if I write out the other details, it will look something like this. And then I will have to put the reflection coefficient for the reflected field, and then I will have e to the beta IXX. Okay, and then I will have to mesh this to the tangential component of HT. Okay, if you write down carefully that thing, you get beta TZ over omega mu2 now. Sorry, this is mu2. Okay, you get mu2. And then TTE, e to the minus J beta T XX. Okay. By setting Z equal to 0, you have to set Z equal to 0 to mesh the components. So this is just the reflected field, and then this is the, actually this is the X component of the incident field. This is the X component of the reflected field. This is the X component of the transmitted field. Okay, so there are two equations and two unknowns now. The first equation that we obtained was this one over here. The second equation that we have now would be this equation over here. So we have two equations and two unknowns. I forgot to put in a E naught here. Okay, there should be an E naught somewhere. Okay, the E naught cancels out, so it doesn't matter. Furthermore, we are going to say one more thing. We say that if you look at these equations, the first equations that we have, okay, over here, equations 1. Maybe I should call this equation 1 since it's important. Okay, and it has to be satisfied for all x. Okay, it has to be satisfied for all x. And the only way that this equation can be satisfied for all x is for these betas to be the same. Can you see that? So unless the betas are the same, they cannot be satisfied for all x. Okay. Second equation, the same thing holds. I need this equation to be satisfied for all x. The beta must be the same. So I immediately conclude that by eyeballing the equation, beta ix must be equal to beta rx must be equal to beta tx. Okay, this is called phase matching. Okay, otherwise the boundary condition cannot be satisfied. Physicists like to call this momentum matching, because momentum is the same as phase to them. The beta vector is also called the momentum vector. Okay, so we have this condition, and from that actually you can learn a lot of things. You can get Snell's law out of this thing. We'll discuss a bit about that later on, because I will talk about Snell's law later. Okay, but then it also allows you to cancel these terms out, because all these are the same expressions now. Okay, and then I can cancel the E naught because they're just common to all of them. And then I can almost cancel the omegas out, not the mu's though. Okay, so if you look at your equations that you have now, the first equation, you can also cancel the phase out because they are now the same phase. Okay, and then what you have is actually two simplified equations. The first equation gives you from the previous slide over here, 1 plus RTE is equal to TTE. Okay, that's from equation 1. Equation 2, which is the second important equation, if you do things correctly, you get beta IZ over mu 1 minus RTE is equal to beta TZ over mu 2 TTE. I forgot to mention one thing though. I have switched this to beta IZ. Actually, I did it wrongly. To be kosher, I have to keep this to be beta R. That means if to do the thing carefully, if I cross my T's and dot my I's carefully, then the second term should actually have beta R. Okay, beta R, which means that this term here should be beta R. Okay, and this term here should be beta Rx. If I had been careful about what I did, okay, I was not too careful, so I just wrote them as beta Ix. But we know that these are plane wave solutions in two different regions. Because they're plane wave solutions, it has to be true that beta Ix squared plus beta Z squared is beta 1 squared. And that is also true for the reflected plane wave. So beta Rx squared plus beta Rz squared must also be equal to the same constant. Okay. And then in region 2, I have a different relationship. These are called the dispersion relationship for plane wave. Since In region 2, I will have a different relationship. Then I will have beta Tx squared plus beta Tz squared is equal to beta 2 squared. Okay, but if you eyeball these two equations, okay, we already argued that by phase matching, these two are the same as each other. Okay, these two are the same as each other by phase matching. Then the only way that these two equations can be satisfied is that beta Iz has to be equal to beta Rc. Okay, but here I cannot claim that. Even though I can say that beta Tx is the same as beta Rx, I cannot claim that beta Tz is the same as beta Iz. So I have to keep this distinction here, but I can make this beta Rz to be beta Iz and take it outside the factor. Then I have two equations and two unknowns that can be easily solved with the notion that beta Tz is not the same as beta Iz. Okay, so two equations, two unknowns. It will be straightforward algebra. You can solve them. I'm not going to go into the detail of solving them, but I just tell you the results. Okay, RTE after solving them would be something like beta 1z over mu1 minus beta 2z over mu2 divided by beta 1z over mu1 plus beta 2z over mu2. Okay, so these are reminiscent of what you learned in transmission line theory, that you have a reflection coefficient gamma, and that gamma you find it to be Zn minus 1 over Zn plus 1. So it's like difference of two numbers divided by the sum of two numbers. You can always rewrite them so that they look like the transmission line equations. Okay, and over there you can also write this as Zl minus Z0 over ZL plus Z0, which is also the difference of two numbers divided by the sum of the two numbers. So this reflection coefficient have similar terms. Okay, then you can work out your TTE. TTE is just 1 plus RTE because you get that from this equation over here, and you can work that in your mind. It would be 2 beta 1z over mu1 divided by this common factor. Okay, in the denominator. But for good mnemonics, I would have to usually write this in terms of the regions 1 and 2. This would be the reflection coefficient between region 1 and region 2. Then in order to memorize this coefficient very easily, I would think of the first term is always related to region 1 and the second term is always related to region 2. And you just take the difference of these two numbers divided by the sum of these two numbers, you will get this reflection coefficient and transmission coefficient correctly, and these are known as Fresnel reflection coefficient. Okay, and it seems that there's another person by the name of I forgot his name, and this was known in the Islamic world around AD 900. Okay, in the Islamic world. Okay, so you can do this for TE polarization. You have all these things that are known to you, and then what happens is that you can do the other polarization, which is TM. And if I look at TM polarization, it is just the dual of the TE polarization, because if I replace E with H, which is minus E and so on, I get the second figure. Again, this figure where it is TM polarization, where the H field is perpendicular to the paper now. So the two problems are dual to each other, and we can apply duality principle, and then hence get the solution right away. Okay, we can get the solution right away by duality. Then then I can actually write down the solution of this TM polarization. Let me draw a line here by duality. Okay, and you can say RTM 1, 2 is equal to beta 1z over, instead of mu1, you use epsilon 1 because you have to do the swap for media as well. Okay, you have to replace the media epsilon 1 with mu and so on. And then beta 1z over epsilon 1 plus beta 2z over epsilon 2. So this is for TM polarization. And then you can do the same for TM polarization 1, which is 1 plus R 1, 2 TM. And you have to be careful, okay, because we use duality principle. These are reflection coefficients for electric fields, because that's how we define them. We define this reflection coefficient to be that for the electric field. So when we use duality principle, this will be the reflection coefficient and transmission coefficient for magnetic fields. Okay, you have to make that distinction because these are not reflection coefficient and transmission coefficient for electric field anymore. So I would like to mention that these are coefficients for H field. Okay, because some textbooks will report the reflection coefficient for the TM polarization for the electric field still. And you will see that these coefficients will look quite different from what I have written down here, because what I have down here is that for the magnetic field. Okay, are there any questions before we move on?